And you guys are gonna love it. I got something for you today. It's gonna make the video so much better. Okay, cool. All right. But I'm trying to leave it charging as long as I can before I make the switch over. So you'll put up with me for a little bit. But just unmute yourself if you have any questions, as always. Thank you guys for being here. Okay, no bells, so let's get going. It is 25. Welcome back. Good to see you. Let's just jump right into that 2.2a homework. Let's just see how we did. See if we have any questions. And please ask questions. I know I talk through these, and maybe that gets your question answered for you, but maybe it doesn't. And if I know a lot of the stuff, I mean, most of the stuff we've done so far has been a lot of the things you've seen last year. But I'm adding little things to it and talking about notation and making sure things look really, really good in a lot of different ways. So if you need clarification, like, it was really awesome. Somebody from cohort A had some questions on last night's homework. And so she and I jumped onto a Google Meet this morning, and we just talked about a couple of things that she wanted to get figured out. And that was amazing. So I want more of that. Less of me, more of you. You guys hear me talk too much. I want to hear from you. So part one, question 1 and 2 was just, let's find some x-intercepts of some functions that weren't factorable. Because I felt like our factoring skills are pretty good, and hopefully you feel that way too. If you're still a little shaky on factoring, we'll need it. So let's make sure that over the next probably couple weeks, my anticipation is I have to look at the calendar to make sure we don't get screwed up anywhere. But I want to take the first half of chapter 2 test. So the polynomial functions test 2.1, 2.2, and 2.3 before fall break. For sure. I want to make sure we get that one in. Okay. So I just have to look at when fall break is. But so I'm thinking maybe either like end of next week, like Wednesday, Thursday, and I don't know if we'll do it in class or it'll be a take-home thing. I think I can trust you all to do the right thing. But Algebra 2 let me down last week when I found out that the take-home quiz that I sent home that they could use their notes on, they could ask me questions on, that the answers ended up on Snapchat. I got sent around. And that just breaks my heart. Like, and now they have to take the whole thing in class on Monday, Tuesday. And so it's more for them, and now we have to go slower. And the people that, it hurts the people that did the right thing, and I just don't want that. So I want to believe that I can trust you to do the right thing. Can I? Okay, good. So don't make me sad, because I'm really sad right now. Okay, part 1, question 1. There's only one x in that problem, so we'll get it, right? Just go solve for it. Solve for that x by adding 7, dividing by 4, taking the square root of both sides, plus or minus. It's the square root of a fraction. And I'm always going to check in a calculator to see if it's nice. There are perfect squares that are fractions, that are decimals. So don't assume that just because it's a fraction doesn't mean there isn't a nice version of that answer. But the fraction of the square root, the square root of a fraction is a fraction of each individual square root, top and bottom. So the square root of 7 is just the square root of 7. Nothing we can do there, but the square root of 4 is 2. And now the denominator is rationalized, and so we can leave it as plus or minus square root of 7 all over 2. Didn't have to simplify a square root, right? Didn't have to do like the square root of 20 becomes the square root of 4 times the square root of 5 to root 5. Like, I can't leave it like this. We'd always have to simplify those radicals. But we don't have to, because 7's prime. Not only does it not have a perfect square factor, it just doesn't have any factors besides 1 and 7. So number 1, I wanted to just make sure that if you see just one x in the problem, just go get it. Really easy to set that thing equal to 0 and solve. But if you get to something like number 2, that's a quadratic trinomial, right? We've got more than one different degree x term in there. You got an x squared and an x. That we can, if it's not factorable, of course, if it's factorable, just factor it, right? But we don't have two numbers that add to 4 and multiply to -6. So quadratic formula or vertex form is going to get that one done. And there's that simplifying of radicals, right? The square root of 40 is the square root of 4 times the square root of 10, which is 2 root 10. And so if you use a quadratic formula, you'd have to simplify there so that the numbers on the outside of that radical can still be simplified, right? You can get yourself, here, I'll use the mouse so people at home can see what I'm talking about, right? I can't do like the square root of 40 in the 6. I can't simplify numbers inside the radical with numbers that are outside. But once I do simplify the radical itself, then I've got 2 6, which is 1/3. So there's a little hidden 1 right here where that mouse cursor is, which is really nice. And look at vertex form. You didn't have to do that simplifying of radicals. Now, that's not always going to be the case. Sometimes we'll have to, depending on where the vertex is. And so I don't know that with this question that one is faster than the other, because we're just like jumping to the last question when we look at quadratics, right? It's not part A, what's the y-intercept? Part B, what's the orientation? Part C, what's the vertex? Part D, where's the axis of symmetry? Part E, what's vertex form? And now finally part F, solve for the x-intercepts. So we hadn't done all that work yet, so you had to find the vertex first. Write it in vertex form and then set that equal to 0. So I don't know, you get to choose whichever one you like better. But when we get to next week or the week after, probably, when we take this first half of chapter 2 test, you'll have already done most of that work, right, to get to vertex form. And so I like the one on the right personally if I have a choice, but the one on the left is always going to work too. Even if it's factorable. Vertex form and quadratic formula are always going to work, but I like to factor if I can. It's just simpler. Questions, 1 or 2? Sweet. Okay, moving on. So part 2 was, all right, you saw some sum and difference of perfect cubes. Let's make sure we've really got it. And so 3 and 4 worked out nicely because it was just ready to go. I just had to figure out what each base was. And so I don't know, like saying x cubed minus 1 is x cubed minus 1 cubed. I don't know that you really need to write that down, but it helps some people, so why not? But for 4, I really encourage you to do what I did in that first step by saying, okay, it's 2x cubed to get me to 8x cubed. And 5 cubed is 125. And then I can factor it because then it's just a squared, b squared. Same opposite, always positive for the sign, spells out soap. Let me just make sure that I'm doing all the right things on this meet before I get too far. Recording and presenting. Okay. But what did we need to do on 5 first? Like, that's not the difference of cubes. And that's the first thing we always have to look for. When we're factoring, a GCF has to come out first if it exists. And so I had to pull out that 3x to the 4th to begin. And then I see what's left behind. And if what's left behind, there's nothing I can do, then fine. Then my factoring is done. Maybe the only factoring you have is GCF, but maybe it's not. Right? Maybe what's left behind is a quadratic trinomial. Cool, I'll factor that with what adds to b and multiplies 8 times c. Or maybe it's the difference of perfect squares, right? X squared minus 9. Or maybe it's the difference or sum of perfect cubes. But this one was a little bit trickier because it wasn't x cubed minus 8. It was x squared cubed, right? Because when you have a power raised to a higher power, we multiply those numbers together, and that's what gets me to 6. So when you're thinking about what base should I put with a power of 3 on the outside that's going to get me to x to the 6th, this number, that 6, right there, whatever that exponent is, had better be a multiple of 3. Because if it's 3, 6, 9, 12, 15, 18, 21, 24, and so on, then that came from a nice base with just a different exponent that got you there. And so if I write it as x squared cubed minus 2 cubed, then it really helps me get the rest of this part factored, right? There's a, there's b. A, b, a squared, a, b, b squared. Same, opposite, always positive. And it just takes a little bit of practice. Now this is Friday, Tuesday, Thursday. This is now the 3rd day of us looking at sum and difference of perfect cubes. So hopefully you're starting to get the hang of it. It'll keep coming up. It'll be kind of part of what we do in 2.2 and 2.3 for sure. And then 2.5 and 2.6. Thoughts, questions, concerns, worries? Did anybody get 5 right the first time? Okay, good. So that's not bad. I was hoping half-ish would really get there. But if you're the kind of person, if I'm talking to you and you didn't get 5 and you just kind of like, you did your best, maybe you pulled out the GCF and you just got stuck. I need to hear from you last night when you were doing that. I got 5 messages last night about that problem, which was awesome. I probably should have gotten 30. Okay. I want to hear from you in the moment where you get stuck, not when you get to class and then suddenly you see the answer. Because I want you to learn how to do it, not see the answer. That makes sense? You're not going to learn as much if I do it for you. Okay. So I want to hear from you in the moment when you're working on homework and you get stuck on something. I want to hear those questions. I got a lot of them last night, more than I ever have, which was amazing. Okay. So let's get in the habit of that. All right. I am the kind of person that wants to be up late helping you. That's who I am. Okay. And then here's part 3. Just some end behavior stuff from last time. Okay. And you see, I just wrote down the function and I wrote the only 2 things that mattered. The parity of the degree, whether it's odd or even, and then the sign of the leading coefficient, which of course is a sub n. Okay. And I should probably have listed those 2 important details in the other order, because I'm always going to look at the leading coefficient first, because that tells me what my right arrow is doing. If my leading coefficient is positive, my right arrow is going up. If my leading coefficient is negative, my right arrow is going down. Then I look at the degree to decide, should it be the same or should it be opposite? Okay, so leading coefficient was positive, degree was odd, so right arrow going up, degree is odd, so odd opposite. Number 7, degree was even, but I don't look at that first. I look at the leading coefficient first. Leading coefficient negative, so my right arrow is going down. Degree is even, so it's the same. Down, down. And you can just say down, down, or up, or down, up, or whatever it is. I like to draw those little arrows because what we're going to do today, what we're going to do all through 2.2 and 2.3 is sketch these things out. Like we started one on Tuesday, right? Sort of. We didn't sketch anything, I know, but we started looking at that x cubed minus 2x, or minus x squared minus 2x, like that. Okay, and that's what I want to do. I want to jump right back into there. But any questions about this? It should be old news, right? Last year? Okay, I know it's old news stuff. I promise new stuff is coming. But if I just jumped into the new stuff and expected this, I think we'd be in trouble. So I appreciate your patience with me as we get down to some new stuff. I'm going to bring the folks at home along with me, but I want to freeze for you the question that we were looking at, which was this one. So we got that to look back at in case we ever needed it. But here comes the nice part for the folks at home. I got a new web camera, and it is amazing. Hopefully, I hope. Period 2 loved it. They're like, it's so much better quality. So, in we go. Okay. Now, what I just need to do is change my video to maybe I have to. I did this last time. If you're at home, make sure, I know it's after 10 o'clock now, so if you didn't take your attendance at home, make sure you drop your name in the chat. Video. Why aren't you giving me the other option? Camera on. Settings. Video. There we go. Ta-da. Oh, it's so nice. Okay, so let me know if you have issues seeing, but it should be so much better quality. All right, let's take a look at that function right up there. X cubed minus x squared minus 2x. And let's do more than just finding the real zeros. Let's kind of do a bunch of things that will help us get to the point where we can sketch these graphs. And a great place to begin is at the end. Let's think about the end behavior of this function. Let me know if you have any issues seeing at home. I'm going to try to talk through it as well. I know there's a little glare at the top right up there because of the light. So I'm going to try to work below that. Up, up, down, down, up, down, or down, up. leading coefficient is positive, so I know my right arrow is going up. Odd degree, so opposite direction, so I know I'm going down like that. So down, up. And that's enough. You don't have to tell me why. You can say like I did for the homework. You can say, oh, the leading coefficient is positive and the degree is even or odd. That's cool too. Where's the y intercept? Well, no, x is 0 if I'm on the y-axis. The constant at the end, right? A sub 0, this hidden plus 0 at the end that obviously we don't need to write, but it's there, plus 0, so just 0. Cool. All right, now the good stuff. Where do we run into the x-axis?
What are the exponents again?
X to the third. There's a question at home. X to the third minus x squared minus 2x. So 3, 2, 1. And this is right from your textbook, example 4 in section 2.2. So if you're at home, you can always just open up the textbook because every question we're going to look at today is right out of the textbook because they're good ones. Okay, x-intercepts. What should we do to find them? One of them is definitely 0, right? There it is. So I know I better get 0 when I do this whole process. So I know what one of them are. Cool. How do we find the other ones? But before we can factor, we need an equation worth factoring. Set it equal to 0 first. Okay, I want to see that very first step where you take this and you set it. And obviously, I'm not going to put the plus 0 anymore, but we'll set this thing equal to 0. Now, that sounds good. So first kind of factoring that we're always going to try is we'll take out the greatest common factor. And we know that between x cubed, x squared, and negative 2x, that there's no number in common. So there's no constant that we're going to pull out. But if you've got a power of 3, a power of 2, and a power of 1, how many x's can you take out without taking too many? Just one. Cool. So take out the x, and then we just figure out what's left behind. And that whole left behind thing is really just going to be what will hopefully continue to factor if we don't have linear factors. All right, so you take out an x. Okay, so x squared, negative x, and minus 2. Now, 2 different powers of x. So I don't want to set this equal to 0 and try to solve for x because I've got different powers. So if I can, I want to keep factoring. If this was just x squared minus 2, done. 1x, I can solve for it directly. But when I think about like splitting this apart and setting separately, both of them separately equal to 0, I can't do that yet. So let's see if we can keep going. What kind of expression is that? Power of 2, right? It's quadratic trinomial. And so that's one of the things that we're going to have to be comfortable factoring. And that's why we spent all of that time in 2.1 working with quadratics, right? That's where we do our, what 2 things add to b and multiply to a times c, and we do our whole factor, right? And because the leading coefficient is 1, the factoring is relatively simple. We don't have to worry about the box or factoring by grouping. What 2 numbers add to negative 1 and multiply to negative 2? Negative 2 and positive 1. So that helps me get my factors, right? Negative 2 and positive 1. I'm going to bring look at me. There we go. Okay, cool. Then break it apart. But we've got 3 unique factors. So I've got 3 unique x-intercepts that I will all just kind of separately set equal to 0 and see what I get. Well, x equals 0 is done. X equals 2 and x equals negative 1. And what 2.2 starts to get us into is stuff you've seen before, is how to sketch these things relatively well. I know example 4 just says find all the real zeros. Okay, we would be done, right? 0, 2, and negative 1. But let's take this one step further and let's sketch this thing out, okay? And what I wanted to come up with is a nice collection of ideas as to what the kind of most important things are when it comes to sketching polynomials. I'm hoping that some darker colors might stand out a little bit better. Okay. So we're going to need ourselves some axes. So, and you can just freehand it. Just draw yourself a pair of axes. I don't know that that's any better. If you ever want to buy me something, I like mocha coffees and expo markers. That's all I need in life to live. Okay. Anything chocolate flavored and expo markers. That's what keeps me going. This is just really bare bones stuff when it comes to sketching axes. We need to set up our axes. What are we missing? Before I do anything with my intercepts and my end behavior or anything, we need to make sure our graph at least has the bare minimum on it. Scale. I need to know what every box is going to be worth. Now, if you're doing this on graph paper, it's a lot easier to separate your tick marks nicely. If you are drawing this by hand, you can break out the rulers, really mark those off, or you can just freehand them. Freehanding is not going to look as nice, but we need to make sure we can plot all the points that matter. And you are looking at a list of all the points that matter. We just need intercepts. I don't need a single other point on this graph because we're just sketching it. And we can't figure out like turning points where it like goes up and like, takes that turn without calculus, not yet. And I want to do this without a calculator's help. So I need to make sure that I can fit 0, 2, and -1 on this graph somewhere. Okay. And what I do, bless you, is I make sure I at least have 1 or 2 tick marks beyond those on either side. So my furthest one left is -1. I just got to make sure I go to at least -2, -3. Furthest one on the right is 2. I got to make sure I go to at least 3 or 4. So I'm going to do like 3 or 4 tick marks on either side. So I'm going to go 1, 2, 3, 4, 1, 2, 3. It's good. Okay. And then put a scale. Every box, in this case, makes sense that it's worth 1. Now, if you want to put 1, 2, 3, 4, -1, -2, -3, that's up to you. But the moment you tell me what one box is worth, now I know that every box is worth 1. You could have gone to the second one and put it 2. Now every 2 boxes is worth 2. That seems like a little crazy. So I just go like that. I need a y scale as well. What's the only y value we have in this whole list? I don't need a y scale then. If your y-intercept was 12, then you just go like that. If your y-intercept was 3,000, go like that. That's fine. Your y scale and your x scale are probably going to be different when we deal with polynomials because these things are going to grow and shrink really fast, okay? But we don't need it, okay? So set up your axes. I need a scale. Good. What else do I need? Label the axes, okay? Your x-axis is x. And since we are graphing f of x, don't put y. Use the name of the function for your y-axis label. If we were graphing more than one function at the same time, sure, I'd put y and then I'd graph them separately. Okay, so we've got labels, we've got a scale. It's the only thing that this set of axes is missing. Before points. I have to know that we're just looking at a small snapshot of a graph that is infinitely flat, but infinitely large. Now we're ready to go. And here's what I do. I switch colors. That's just me. My axes, my background exists in one color. The graph itself exists in another. Okay. What I do first is I plot my intercepts. And those are the only points that I'm going to need. 0, 0, 2, 0, and -1, 0. If there was a different y-intercept, I would plot that one. But that's all I need. Now, I draw my arrows. I make sure my end behavior is consistent with what I thought was true from the beginning. Now, but here's the thing. If my intercepts exist within this space, should my arrows like be drawn inside them? Like in here? No, it's got to be on the outside. right? And so what I usually do when I graph these things is I'll go like one box to the to the left of the left one, and one or two boxes to the right of the rightest one, and that's where I'll draw my arrows. So here's my left, my point that's furthest to the left. So I'm gonna go like one box or two, and I'm just gonna kind of come way down here, and I'm gonna draw my arrow, disconnected from the point itself. But not only is it pointing down, but it's also kicked out a little bit. And I do the same thing on the right. So here's my rightmost point. I'm gonna go a box or two to the right. I go way up here to the top because that's what we figured out. And I'm gonna draw the arrow up there. God, these pens. So many choices. Okay, and now all I have to do is connect from left to right. And I start at this left arrow, and I'm just gonna work my way through those intercepts, not worrying necessarily about where all the other points are. So I started this arrow, okay, I connect, I know I gotta go through this x-intercept, so I cut through it. Now, just for a second, I'm just gonna pause for us. I have to get back down to here somehow. How am I gonna do that? I have to turn, right? Where should we turn? Without calculus, we don't know. We don't know where that turn happens. So what I usually do is I go about halfway between the x-intercept that I just crossed through and the next one that I'm gonna go to, and I'm gonna take a turn. And because they're polynomials, what kind of turn should I take? A smooth rounded one or a sharp one? Smooth and rounded, good. So about halfway, I don't know where, I don't care where. I turn, I take a change, and I cut through, and I cut through. And I say, okay, I pause for a second, and I say, all right, I gotta get to my next x-intercept, but I've gotta take a smooth, rounded turn. I go about halfway somewhere, and I just smooth and round, I just take a turn, and I make sure that I cut right through. And I get to here, and I say, well, I'm out of x-intercepts, which means I just have to get myself to the arrow. Good, the arrow's up there. I'm going to connect it. If I don't feel like I love the way it's drawn, I erase it, I clean it up, I make it look nice. And then I check to see how I did. And so what I'm gonna do is I'm gonna share it home, but I'm just gonna turn around so you all can see it. I'm gonna jump into my calculator right now, and I'm just gonna see what it looks like. So I'm going to y equals, I'm erasing what I have in there. I'm gonna type in x to the third minus x squared minus 2x. I'm gonna zoom standard. And it looks pretty good, right? That's pretty good. And that's all I want us to be able to do. But we can't use this to do it. And I wanna make sure that our graph makes sense without it. Okay, and that's my process. That's what I'm thinking. I think that should work out really well. Okay, let's do another one. Let's take this up a notch. Okay, I'm gonna stop presenting. We're gonna go over here. If you don't want to be in the picture, you can go to either red desk, that's fine. But if you don't mind, you can stay. But that's what it looks like. That works. Totally up to you. There you go. Okay, cool. I am gonna pull up a question here that I like. Let's see, it's gonna be the next one. Okay, this is example 5 in the same section. Example number 5, and it is f of x again. F of x equals negative 2x to the 4th plus 2x squared. And let's do all the same things we just did. Let's get end behavior, y-intercepts, x-intercepts, and then we'll sketch it. End behavior. A great place to begin is at the end. Okay, I know it's a little glary at the top there, but that says f of x equals negative 2x to the 4th plus 2x squared. Okay, up, up, down, down, up, down, down, up. Negative leading coefficient, so down on the right. Even degree, so same direction. Down, down. Okay. There's only ever going to be, at most, one y-intercept, and because all of these functions are continuous forever, there's going to be one. Where is it? Yeah, plus 0 here at the end. There's no constant. That a sub 0 term is missing, which means it must be 0. Okay, x-intercepts. There might be 1, there might be 0, there might be, who knows? Right, it could be 0 because if my arrows are both pointing down and this thing exists below the x-axis, there might be 0, but I know one of them for sure, right? But let's find the rest. Negative 2x to the 4th plus 2x squared equals 0. First kind of well, two different powers of x, so I know I can't solve for it directly. So I got to go to my factoring. First kind of factoring we'll always do, take out that greatest common factor. So what is that GCF? 2 for sure, and between my two powers, I just take the smaller of the two, x squared. But because your leading coefficient is negative, I highly suggest your greatest common factor, pull out the negative with it, so that when you get into here and you talk about what's left, now your leading coefficient is positive, and factoring might have just gotten a whole bunch easier. Okay, so if your leading coefficient is negative and you're pulling out a GCF, take the negative with you. Okay, what do we have left inside after we take negative 2x squared from both? X squared, because that'll get me to here. And now 2x squared, I took out negative 2x squared, so minus 1. And now I look inside. You come with me for a quick second. God, I love this thing. It's so nice. Hopefully you can see that okay. Is that a quadratic trinomial left inside? No, what is that? It's the difference of squares, right? It is the difference of two squares, what I'm going to call dots. Okay. If you got the difference of two squares, that is perfectly factorable. God, I can maybe move you closer so you can see more. There we go. Hopefully that's a little better. Let's factor. 2x squared stays out there, and it's perfectly factorable. Square root of the first one goes first. Square root of the second one goes second. One's a plus, one's a minus, and the order doesn't matter. And again, I look at my factors now. And I say, okay, I've got three different factors. Negative 2x squared, x plus 1, and x minus 1. Is there only one power of x in each one? Right, there's an x squared, and it's the only one. There's an x, it's the only one. There's an x and the only one. It's as factors as it needs to be. Now, I can break it apart and deal with each one separately. Negative 2x squared being equal to 0, x plus 1 being equal to 0, and x minus 1 being equal to 0. Now, I don't know that I need to see that step written out. If you want to just jump right to the answers, that's cool. Let's divide both sides by negative 2. 0. Let's take the square root. 0. There's 1. Subtract 1, so negative 1. Add 1, so positive 1. And now we're ready to sketch. And freehand is okay. Obviously, use some tools, it's going to look better. It's going to look nicer. When it comes to test time, on the test itself, I will put a section of graph paper. I will print graph paper right on the test so that you don't have to worry about measuring stuff out. You can just mark your tick marks as you need, and that's all we need, right? I got to set up my axes, so I need a scale, I need arrows, and I need labels. And I just got to make sure I can fit all of them. So I really just have 0, negative 1, and 1 that I have to fit on here. So I don't need more than like 2 or 3 boxes in every direction. We'll go 3. I like some space. 1, 2, 3. 1, 2, 3. That little wiggle there is driving me crazy. I wish it was straighter. Ta-da, it's a little bit better. Not great, but I'm not going to worry too much about it. Arrows on my ends. Labels, x, and what's the name of the function? F of x again. Cool, so I'll put that at the top. Do I need a y scale? Not with a y-intercept of 0. If it was 10, 12, negative 3,000, whatever it is, then I would just put that one point. That's the only point I would need. And we'll get to practice. It looks like that too. Put a number, though, so you know what every box is worth. And if you want to put 1, 2, 3, negative 1, negative 2, negative 3, that's cool. Maybe you want to mark off the x-intercepts. Like I'm going to put, like maybe on this one you put, maybe you just put negative 1 and 2. That's cool, right? You have plenty of freedom as to how you do it. I just need to know what every box is worth. That's all that matters. Okay. Number one, set of axes done. Number two, let's plot some x-intercepts. So I switch colors. My graph and my scale, although in the same plane, I want them to stand out. So that's what I do. Totally up to you, but I'm going to mark off -1, 0, and 1. Okay, intercepts done. Arrows / end behavior. Okay, so there are my arrows, right? I know I'm going to go down, down, and I just go on the outside. I just go a box or so past the one on the left and the one on the right, and I just draw them going down, in this case, and out, down, and out. And I give myself some space to do that. And I leave them disconnected for now because I have to connect from left to right. And so I just go for it, right? I'm gonna cut through this one. Cool. Now I have to take a turn somewhere, so I go like halfway and I take a turn. Cool. I come down. Awesome. I take a turn about halfway through and I cut through and I. But so here's my end behavior, right? My arrows are good. My x-intercepts are good. But clearly something went wrong in the way that we connected them. And so Lydia just went like this. Why? Why are you saying that something different needs to happen right there? We know we got to end up coming down. But the question is, like, where should that change happen? Should it, like, maybe what if I went like turned here and then went through and then came down? Like, how do we know? So obviously we need to back this thing up. How do we make that choice as to where we connect, where we intersect the x-intercepts differently? Take a look for a second. Sorry. All right. Take a look at the degree of each factor. What's the exponent right there? That we don't, right? Okay. What's the exponent right there? Which is really like right out here, right? There's a 1 right there. What about this one? And how did we cross through each one of those x-intercepts? If you like were to blow up those 3 circles and you just looked inside and ignored everything else, what do those purple graphs on the little just inside those green circles, what do those all look like? Just that space. If you could like pinch and zoom and blow up just what's right there, what does that look like? What shape does that look like in there? Just looks like a line, right? Linear, linear, linear. Look at the factors of each of your x-intercepts here. The x-intercept, I'll go back this way. The x-intercept that happens at 1 came from this factor, which came from this factor. What's the exponent out here? This x-intercept came from this equation, which came from this factor. What's the degree of this factor? This x-intercept came from this equation, which came from this factor. What's the degree of that one? The way you intersect your x-intercepts depends on the degree of that factor. And so if I'm looking at, how should I say this here? Okay, let's do it this way. Let's just graph it. If I'm going to connect this arrow to this x-intercept, I have to check the degree of that factor that got me there. If the degree is 1, I will cut through it like a line. The degree of this factor that got me to this x-intercept is degree 2. What kind of graphs do we see that have x squared in them? And so what shape is that graph? Parabola. I need to intersect that x-intercept like a parabola would. That's where that turn happens. Now I take a turn and I head back down. So I kind of pause as I approach each x-intercept, and I look back at the degree of each factor. So I look at 1 and where it came from. The degree is 1, so I'm going to cut right through it. Now I can intersect the arrow in the direction that I was kind of expecting to do that. Okay, what is that called? Where the degree of each factor that's you. You can stay there if you want. What is that called? The degree of each factor affects the way it hits the x-intercept. Starts with an M. Magnitude? No. That's a good guess, though. That's a good math word. Magnitude is size. So this pen has a magnitude. It's the length of that pen. Close. Multiplicity. Nice. The multiplicity of the zeros, which is just another name for roots, which is another name for x-intercepts. The multiplicity of the zeros. The degree of each factor describes the behavior of the function, which I'm just going to say f of x, but it could be whatever function it is, of f of x at the x-intercepts, at each x-intercept. So each individual degree changes the way we're going to run into the x-axis at that spot. Okay, and so that's what I want to do. I just want to look at, okay, if we compared degree to behavior, and let's give it a name. So if our degree is 1, what kind of function is that? Linear, right? So we'll call that linear, which means that the behavior at the x-intercepts, so I'm just going to draw, the line. It could just cut right through it at the x-intercept going up, or it could just cut right through that x-intercept going down. So you're going to intersect your intercept. It's weird to say that. Just like a line would at that spot. Okay, so what if it's 2, right? The name is parabolic. Parabolic. The function is quadratic. The shape is parabolic, and that's what I care about is what it looks like, right? 2.2 is, what do these graphs look like? Well, that means I'm going to run into the x-axis, and I'm going to make my turning point that x-intercept. Now, it could happen from the bottom, too. It depends on what direction we're flowing, and that's why when I say step 4, connect from left to right, that is so crucial that you start on the left and go to the right so that you intersect them from the right direction. What about degree 3? What kind of function is that if it's got x cubed? What do we call that? Cubic, yeah. But do you know what those graphs look like? Like if I drew just y equals x cubed, I love when I ask that question because like half the class always just uses their hand to do it because there's no better way to like draw that thing out, right? If it's just plain old x cubed, it comes up quickly, but then it flattens out near the x-axis, cuts through, and then symmetrically, it's odd, right? So the symmetry through the origin, it goes through that way. Now, so it could go up, turn, and go up. Now, it's always increasing. It doesn't come up, down, and then go back up again, okay? But the perfect middle is where that x-intercept is going to be. Or it could be going down, right? It could come down, flatten out for a second, and then head back down. And that perfect middle, when it's at its flattest, that's where that x-intercept is going to be. And then tomorrow we'll look at what happens with degree 4 and 5 and 6 and 7 and 12 and 100 and 90,000. They're all gonna, you're looking at all of our options. They just happen faster. Okay. Now let's see how we did. I'm just gonna jump in the calculator. If you have one in front of you, you could play along too. I'm gonna present at home. Open up my calculator, and I just want to see how we did. Negative 2x to the 4th plus 2x squared. If I leave it as, oh man, what'd I do? Y equals. What didn't they like? Oh, I put a minus instead of a negative. If I leave it as Zoom standard, it's kind of far away from the action that's happening really close. I mean, look at our scale here, right? Much closer. So I'm going to zoom decimal because that goes like -4 to 4. That's pretty good, right? That's really good. That's a very good sketch of this graph. Okay, and that's all we really need to be able to do is match those two together, right? Folks at home, nice, right? I like, oh, you're looking at this. Nice, right? Pretty good. Okay, cool. Let's just do one more. We'll call it a day. Let's do one more. I'm going to erase that one right there, and we'll do this. Okay. This one is going to be example 8. So I'll leave this up for the folks at home to see just for a second, and then we'll go from there. So let's just do one more because we're out of here at 15, right? Okay, cool. So we have those 5 minutes. Perfect. That's exactly what I need. All right. Here it is. They call it f of x again. This is example 8 out of this section. I like it. It's a good one. 3x to the 4th minus 4x cubed. And let's do it all. End behavior, y-intercept, and x-intercepts, potentially plural. Okay, f of x equals 3x to the 4th minus 4x to the 3rd. I'm going to stop sharing so my screen gets bigger. Okay. And then we'll sketch it. Let's go quick. And behavior. Good. Positive leading coefficient, so my right arrow goes up, even degree. So there we go. Y-intercept. 0, 0 again. X-intercepts, let's set this thing equal to 0. More than one power of x, so I know I have to factor. Greatest common factor first. X cubed. What's left behind? 3x minus 4. Only one power of x here, only one power of x here, so I am ready. I'm done factoring. I set the first one equal to 0. I set the second one equal to 0, and we solve. So I get x cubed is equal to 0. Take the cube root of both sides. Still 0. Of course it is. Add a y-intercept at 0, 0 again. We'll get to some different ones, I promise. And then 3x minus 4 equals 0. Solve it. It's just linear. Add 4, divide by 3. Best way to write that number is 4/3. And so when I design a scale for this graph, right, labels, axes, all that good stuff, arrows, I want to make sure that I plot exactly 4/3. If I've made a scale where every box is worth 1, could I perfectly plot 4/3? Can't do it. So what scale could we use to make that work? Go by thirds. Make it 1/3 and then go 4 boxes, and there you are at 4/3. What's another option? 1/6. That's a lot more boxes, right? What's another option? 2/3. Nice. Then every 2 boxes, right? 2 boxes would get me to 4/3. What's another one? 12/9. How about 4/3? The only point on the x-axis that's not the origin, let's just make that The only number that matters. Now, you got to make sure that whatever scale you choose, you can hit every point. So if I have 4/3, but I also have 2, this is not a good option, right? I'd have to go by like 1/3 to do that, or 2/3, so that I get there. But that's good. That's enough for me. I don't need a y spot. This is f of x again. So every box is now worth 4/3, and I only have a couple points that I need to plot, right? 0, 0, and 4/3. Set up my axes, done. Plot my intercepts, done. There's only 2 of them. Arrows and end behavior. To the left of the leftmost point, to the right of the rightmost point, and up they go. Now, that's a little close. I got to go at least a box, so I give myself some space to worry about the multiplicity of my 0. Okay, so as I come down to here, I have to stop, pause, and say, what is the multiplicity of the factor that got me to that 0? I better hit it like a cubic, which means I need to come down, hit that graph like this, and then head off. Okay, and I probably could have done that even more dramatically so that it stands out. Exaggerate that movement. Got to take a turn somewhere. I turn about halfway. I stop and I say, what's the degree of the factor that got me to that 0? That's how I know how I'm going to hit it. Now, my arrow's a little bit far to the right with the flow that I had as I was graphing this, so get rid of it. Just, you have an eraser on your pencil. Use it. There's our perfect graph. Done. See ya. Probably just going to say, join me live tomorrow, but no work you need to do for tomorrow. Just be there. Okay, thanks, everybody. Questions at home? How do we do? Thank you. See ya.
Good. Thanks, Mr. Rosengrant.
Anytime. Thank you guys for being there. I appreciate it. If you have questions, just let me know. I keep looking at my screen, but you're there. How was the quality? Was that better? Was the quality of the screen better?
Quality was
better.
way better.
Yeah.
Okay, good. I'm glad. So I got this camera. It's going to be really nice. I don't know if you'll be able to see it if I point it. Oh, that's too much. Enter infinity. It's this like whole separate, and I would need a mirror to show it to you, but it's super nice. Okay, cool. You guys are good. Thank you guys for being here. So yeah, just show up tomorrow. We'll be live tomorrow. I'll just kind of keep 2.2 going. We'll just work through a couple more examples, but nothing you have to do in preparation. Peace and love. See ya. Thanks, guys.